So let's go back to our discussion on speed again. So we mentioned circular motion, we're going to focus on speed. So first off, we're going to just present you a number. Earth, it's going to rotate around the sun at an astonishing speed of 107,000 kilometers per hour. Now, the skeptic in you might say, well, Mr. O'Donnell, where did you get that number? Like, you just threw that out there. How do we know that's valid? Excellent question. So we'd like to show you that. Now, we're going to make a bit of an assumption here. And the reason we're doing it makes your life a little bit easier. We are going to assume the Earth, its orbit around the sun, is a circle. In reality, it's actually an ellipse. Earth's orbit around the sun is quite close to being a circle, but it's not exactly a circle. So we are going to shortcut this a little bit. To help us out, we are going to go back to uniform motion. Now you might say, Mr. O'Donnell, there's acceleration. We can't use uniform motion. It's one of those we're going to call this a loophole / lawyer's trick. The speed itself isn't changing. So if the speed itself isn't changing, we can use v equals d over t. Anytime I've hounded you about using v equals d over t, you had used it in a context where the speed was not constant. The speed was actually changing. Since speed isn't changing, we can use v equals d over t. We can get away with that. Now, for anything in a circle, we have to fill in the gaps. What's d? What's t? Well, if I have any orbit here, here's my lovely orbit. If I know the radius of it, well, first of all, we know that the distance around here, this distance around the circle, that's what you've learned as the circumference. So you've probably learned it as 2 pi r or pi times the diameter. We generally deal with radii and astrophysics stuff, so we're just going to say the circumference is 2 pi r. In terms of the time frame, we're usually also interested in the time it takes to do one complete revolution, which we've called the period. So d, we're going to swap out for circumference. T, we're going to swap out for period. What that's going to do is that is going to give us an equation for the speed of an object in circular motion. So what we're going to get here is we're going to get v equals 2 pi r divided by the period. So v is our orbital speed in meters per second, r is our orbital radius in meters, t is the orbital period in seconds. So it's a very versatile equation. It's going to help us out quite a bit in circular motion. You don't need to know how to derive this equation. It is on the data sheet, so don't spend your time trying to derive it when you need it. So now that we have an equation for speed, let's move on to the next part. So we talked about, even though the speed itself isn't changing, the velocity is, because that direction's always changing. And we said if the direction's changing, and hence the velocity changing, we have to have an acceleration. Now, there's some geometrical proofs for this. We aren't going through it. If you want to see it, you can certainly find them online. But to kind of cut through all of that, in order to calculate the actual magnitude of this centripetal acceleration, so that change in velocity directed towards the center of the circle, we have this equation here, which is just equal to v squared over r. So AC is the magnitude of our centripetal acceleration. V is going to be our radius, V is going to be our speed in meters per second, and r is going to be our radius in meters. So the only thing that's going to affect our centripetal acceleration is the speed and the radius. Now, you might say, Mr. O'Donnell, can I use that v equals 2 pi r over divided by t here? You absolutely can, and we're going to show you that in a little bit. That is actually a really good question. We're going to give you another form of this equation. Now, we spend a lot of time talking about the magnitude of the centripetal acceleration, just because in every single case, the direction of centripetal acceleration is towards the center of the circle. Like 100% of the time, it's not particularly interesting for us to continually make you write that. So, as I said, we're going to focus on the magnitude piece. Let's look at an example of this. So we have a vinyl record, and it has a diameter of 35 centimeters and a rotational frequency of 0.750 hertz. So we'd like to find the magnitude of the centripetal acceleration. Now, first thing is, we gave you diameter. That's the big trick and trap we do here. We want the radius, which is just going to be half of the diameter. So the radius is going to be 17.5 centimeters. But we also need the radius in meters. So there's two traps for one here. So instead of the radius being 17.5 centimeters, we're going to say that the radius is 0.175 meters. So I've tried to get you on two traps there. It's nefarious, but it is what it is. Now, the magnitude of the centripetal acceleration is going to be v squared over r. We know what r is. However, we do not know what V is. So we need to find V. So let's find V. So V is equal to 2 pi r divided by the period. This is the equation that we just got. We know r, but oh no, we don't know the period. So now we have to find the period. And the period we know is 1 over the frequency. So you're seeing that we're going to have to back substitute a lot here. A little later, we'll show you how to do this in one step. You won't have to do all this mess here. Well, the period being 1 over f, well, we're given the frequency. So this allows us to find the period. So if we know that in a second this vinyl record does 0.750 revolutions, or 3/4 of a revolution, what that's going to tell us here is that our period's about 1.333 seconds. So the time for that vinyl record to make one complete circle, it's about 1.333 seconds. Now that we know the period, we can take our value for the period here, and we can input that in our equation for the speed. So now we're going to start to back substitute everything. So then I have my 2 pi times my radius of 0.175 meters, and then I'm going to divide that by my period, which we just found to be that 1.333 seconds. So let's have a look here. What are we going to get? So we are going to get about well, 0.8247 meters per second, roughly. All right, now that we know the speed, we can take that into our equation for the centripetal acceleration. So the last thing is we're going to plug in that speed that we just calculated here, divide it by the radius. I'm sure I don't have to remind you, but the biggest mistake that happens for centripetal acceleration is forgetting the square there. So don't forget to square that speed that we just found. The biggest mistake. Don't fall into the trap on that one. So what we're going to get here, if we square that, divide by this radius, we're going to get about 3.89. And centripetal acceleration still has the same units as acceleration, meters per second squared. So the magnitude of our centripetal acceleration here is 3.89 meters per second squared. Perfect. We don't need a direction, any of that. If you wanted to put a direction, if it didn't ask magnitude, towards the center of the circle, perfect, done. So then the last little piece there that we just want to tack on really quickly, if we have centripetal acceleration, we have to have centripetal force. We know from Newton's second law, the net force is the mass times acceleration. So we said in circular motion, instead of talking about net force, we're going to talk about centripetal force. F net and Fc, they're the same thing. We just use Fc in place of F net when we're dealing with circles. But Fc, if it confuses you, think of it like net force. So the centripetal force is just going to be the mass times the centripetal acceleration. So using that equation we have for centripetal acceleration, v squared over r, we're going to put that in there, and we get that the magnitude of the centripetal force is mv squared over r. This equation is not on the data sheet. You have to be able to construct it from Fc equals m times AC. AC is on the data sheet. F net equals MA is on there. You have to link the two ideas together. So please be aware that the equation for the centripetal force is not on the data sheet. And same thing, we aren't going to really focus a lot on the direction piece because the direction of the centripetal force is always towards the center of the circle. So let's just finish this out with a nice quick example. So let's find the magnitude of the centripetal force. On a 30 kilogram tire, it has a radius of 0.250 meters and it rotates at a speed of 24 meters per second. So our equation for the magnitude of the centripetal force is going to be mv squared over r. We have m, we have v, we have r. I'm not making you convert, nor am I making you do a rearrangement. This is a strict plug and chug. So this is me being really nice. So we got our 30 kilograms. We have our 24 meters per second. Don't forget the square here. So let me put it in pretty pink. And then we get that 0.250 meters. So these are meant to be the gimme questions. We're not making you do anything hard with it, so don't disappoint on these. So we're going to get that the centripetal force is about 6.91 times 10 to the 4 newtons. So that magnitude of Fc, 6.91 times 10 to the 4 newtons. Centripetal force still has units of newtons. It's still a force.